This is the introduction to a series in which I will show how to solve this particular differential equation. I will write it out now. It's a linear first-order non-homogeneous differential equation. Linear refers to the way that the differential operator works. It is here d over dx minus alpha, and were you to have a y1 and a y2 and add them and then apply this, it's the same as applying this to each of them and adding them, and scaling works in such a way that applying this to a scaled version of y returns a scaled version of this applied to y. Now, we may write the equation like this. Y here is a function of x, and the goal is to solve for y. Now, the reason that we may study this particular equation is because for second-order linear non-homogeneous homogeneous differential equations, that is, we may apply this twice, and third order you don't often see, but the same principle applies. Now, our first method of solving this would be by Ansatz. An Ansatz is a guess, it's an educated guess, and this is the German word for guess. Now, our Ansatz will go like this. First we solve the homogeneous version, so that's when the right-hand side equals 0. We solve by taking the term to the other side, dividing through by y, and recognizing that this left-hand side here is in fact the logarithmic derivative of y. And by basic solving methods, i.e. integrating both sides, we have this: y equals ae to the alpha x for some constant a. Now, a reasonable ansatz would be to replace a with a function g of x. I will write g from here on. So y equals now g e to the alpha x, and we'd like to see what happens when we apply d over dx minus alpha to y. Well, if you know the product rule, this is actually fairly simple. We get g prime e to the alpha x plus alpha g e to the alpha x minus alpha g e to the alpha x. These terms cancel, and we're left with g prime e to the alpha x being equal to f of x. Now, we must solve for what g is. This is quite easily seen to be g of x equals the integral e to the negative alpha x times f of x dx. Now, recall that we wrote y equals g e to the alpha x. We may also write here that g equals e to the negative alpha x times y. And so, if this equals e to the negative alpha x times y, then, well, y equals e to the alpha x times this integral e to the negative alpha x f of x dx. This is our final solution. Now, this may be considered an abuse of notation since we have the variable x inside the integral, but also outside. And what should be interpreted here is that we perform first the integration, and then we multiply it by whatever's on the outside. I will show this with an example now. Suppose we have y prime minus 2y equals e to the x. Now, to solve this, we've just got to substitute alpha equals 2, f of x equals e to the x, and we solve by performing this integration here. Y equals e to the 2x times the integral of e to the negative alpha x, where alpha is 2, we'll substitute 2x e to the x dx. The exponent rules tell us that we recombine like this. Those two exponents are added, so we end up with e to the negative x dx, which integrates then to negative e to the negative x plus c. So we have e to the 2x, negative e to the negative x plus some constant c. And finally we have e to the x plus c e to the 2x. Right, now we can check that this holds by plugging it back into our differential equation. That's up there. So we have y prime equals e to the x plus 2c e to the 2x. Negative 2y equals negative 2 e to the x minus 2 e to the 2x. And adding these gives us, sorry, I've missed off a negative there, gives us y prime minus 2y equals e to the x, exactly as we wanted. And so this is the first way of solving this differential equation. Done.